Okay, so now let's do another example. Let's pretend now that we didn't know any of the concentrations in the reactor. So in this original problem statement, we're given Ca, Cb, Cc, and Cd. We're given values for those. Let's pretend we don't know that information, but instead we know the volume is 400 liters, and I'm going to round up from 399 just for the sake of using simpler numbers. Let's pretend we know the volume, but not those concentrations. And now we want to determine we want to determine the exit concentrations of all 5 species. So now our number of unknowns is different. In this case, the number of unknowns is equal to 5. Concentration of A, concentration of B, concentration of C, concentration of D, concentration of E. That's 5. We hence need 5 equations, and those equations are going to be the mole balances for those different species. So we're going to have to write one mole balance for each of them. So that's going to give us our 5 equations. This is another reason why conversion does not work, or solving in terms of conversion does not work. If I write an equation in terms of conversion, that gives me 1 equation, but I need 5. So the conversion equation isn't enough. So, okay, so all these mole balances, they take this form, V is equal to Fj naught minus Fj divided by negative Rj net. So we know this form when we're used to using this equation, with the one exception that we write in terms of conversion, but now we're not going to do that. We can rearrange this equation. So this equation as is perfectly fine. However, it can be easier to work with if we rearrange it slightly. So if we rearrange the mole balance such that we're setting it equal to 0. So in the first example, its volume is equal to something. In the second example, 0 is equal to something. The second way of writing it can be easier, because if we're going to work with a nonlinear equation solver in some mathematical software, most of those only accept equations written as 0 is equal to something. So we're setting ourselves up to do that by rearranging this equation. So setting them equal to 0 sets us up well to use a nonlinear equation solver. Such as fsolve. And what these nonlinear equation solvers do is they find the roots of an equation, which is why they want you to set them equal to 0. All right. So let's prepare to do this. I'm eventually going to solve this problem in Python, but let's prepare to do that. If I want to be able to write the mole balance of the different species, I'm going to need the net rates of the different species. To do that, I'm going to need the stoichiometry matrix and the rate matrix. I'm going to write the rate matrix first, because that's going to remind me what the rate of each reaction is written in terms of. And this is reminding me that reaction 1 is written in terms of species A, reaction 2 is written in terms of species D, and reaction 3 is written in terms of species E. So now what I want to do, because the rates of these different reactions are written in terms of these different species, what I need to do is rewrite those reactions such that the stoichiometric coefficient on the species that the rate is written in terms of is equal to 1. So the stoichiometric coefficient on species A in reaction 1 must be equal to 1. The stoichiometric coefficient on species D in reaction 2 must be equal to 1. And the stoichiometric coefficient on species E in reaction 3 must be equal to 1. So let me rewrite the reactions accordingly. Okay, so now I've rewritten my reactions, and I can now use this to write my stoichiometry matrix. And as I do this, I'm going to recall that the stoichiometric coefficients that I enter into the stoichiometry matrix must be negative for reactants and positive for products. I'm going to have 3 rows in this matrix. The first row for reaction 1, the second row for reaction 2, and the third row for reaction 3. And I'm going to keep my columns in alphabetical order. So this is going to be A, B, C, D, and E. So I've done this for reaction 1 based on the reactions that I rewrote. I suggest now that you pause the video and do this for reactions 2 and 3, and then come back and check. All right, so now we have the 2 things we need to write net rates, and those are the individual reaction rates as well as the stoichiometry matrix. And now we can substitute this into any nonlinear equation solver. I'm going to use Python and Google Colab. The reason I'm going to use Python rather than the Polymath Plus free solver is because when I have multiple reactions, I have a lot of equations, and Polymath Plus is going to limit me to 10, and I'm going to have to do way too much substituting in order to reduce my number of equations down to 10, and I just don't want to do that because I'm afraid I'm going to make errors. So I'm going to use Python, and I will turn over to that in just one moment. So here I have basically the code needed to solve the CSTR problem loaded into Google Colab. So I'm going to solve this using Python, and I'm going to use the fsolve solver. So the first step I'm going to do is load that information into the Google Colab. And I'm going to click this here play button, and that's going to run that piece. All right, so now this cell is solved for. Now we're going to go look at this cell. There's a lot of information here. I'm going to walk you through it. All right, so first I have my given information. So the first thing I did was go ahead and enter the concentrations of the inlet concentrations of the various species. We're told that species A comes in at a concentration of 3 molar and that nothing else is coming in. So I've set Ca naught is equal to 3 and the rest of these are equal to 0. And I could add here units on all of these, which would probably be helpful. Here I have my inlet volumetric flow rate. This is equal to 100, and the units here are going to be something I don't remember, liters per minute, I believe. And then I have my different rate constants. I believe that the units on this one were minutes to the -1. And I don't remember what the other ones are, so I'm not going to write those down. I do suggest, however, that before you enter values into a code that you put things in all consistent units. So for me to do that here, I have done all concentrations in moles per liter, all volumes in liter, and all times in minutes. And if you do that before you enter information in, then it's less we need to worry about units in the actual code itself. I should also note that because I'm using Python, when I use this hashtag here, that anything that's written after that is a comment, so the code does not read it. All right, so I got my rate constants here. I'm using my CSTR volume. That's going to be 400 liters. Next thing I'm going to do is define my stoichiometry matrix. I'm going to call that nu. So we use the Greek letter nu to denote stoichiometric coefficients. So I'm going to call that my stoichiometry matrix nu. The way that I'm going to define it in Python as a matrix is using this np.array command. So np comes from this numpy package here that I've imported, and when I say import as NP. That's how I personally am going to abbreviate it. You have some flexibility here, which you define. It's pretty common to use NP. That's why I do that. But basically what this NP dot array is telling the code to do is bring the array syntax or coding from the NumPy package. So that's what I've done here. I'm then going to define the matrix. So there's some syntax here. I have to enclose whatever I put in here in parentheses, number one. But then number two, I need to use brackets in order to define the matrix. I'm going to use an outer bracket to define the matrix itself. That's these green ones here. And then I'm going to define all of the rows, each in their own set of brackets. So you can see I've done that here. Here's one row, here's another row, and here's my final row. So this matrix is a 3-row by 5-column matrix, which is exactly what we want it to be. And then I'm basically entering in the same numbers here that I just developed for my problem statement. I'm going to need some information about the inlet concentrations and flow rates, and what I'm going to want is to set these up as also a matrix, and this is because I want to write my mole balance as a matrix. So I have here my concentrations are set up as a column vector, so this is going to be a 5 by 1 vector. You'll see why in just a moment. And then I'm also going to set up a initial flow rate vector that's going to be just multiplying my concentrations or my inlet concentrations by the inlet volumetric flow rate. I then have some print statements. I like to do that just to, to make sure the software and I are on the same page about what has been entered. And now I'm going to come in here and I have a function that I've created. I've called this function CSTR. What the function does is constructs a column vector of mole balances for species A, B, C, D, and E. And so it's just going to construct that, and then I'm going to pass that vector to the fsolve command, which is going to find the roots, which are going to, in this case, be the molar flow rates exiting the CSTR. Okay, so basically when I set up a function, I have to have some variable for it. You can call the variable anything you want. Here I've called it x, and then I'm basically saying that x is going to be a matrix, and the different columns, A, B, C, D, and E. So it's going to be a 5-column matrix where each column is the flow rate of a different species. Next, I'm going to start building my mole balance. For my mole balance, I need inlet molar flow rates. I've already defined those here. I need exit flow rates. I'm going to define those here based on the values that I just defined from my solution. And I also need concentrations. This is because my rates are all written in terms of concentrations. So I'm going to write concentration equations in the same way that we're used to, really, in order to create or construct concentrations from molar flow rates. Next, I'm going to write in my rate laws. These are copied from the problem statement. The only piece of syntax here is that Python doesn't use the caret symbol to raise a number to a power. It uses the double asterisk instead. So this is a CC squared term. So I've used the syntax CC double asterisk 2. Now I'm going to create my net rates. So I've already got my stoichiometry matrix. I entered that up here. Here I'm going to write my rate expressions. The reason that I can't define this outside of the function is because it requires values for the different concentrations, and I don't know the different concentrations until I solve for them. So it has to go inside this function. That's why I have to put this here, but I can put the stoichiometry matrix outside of the function. This is going to be a column vector, just like we've been defining it, where the first row in the column is going to be the rate of reaction 1, the second row is going to be the rate of reaction 2, and the third row is going to be the rate of reaction 3. I can then get my net rate by doing the dot product, which I'm going to call with this np dot command, on the transpose of the stoichiometry matrix. So this dot capital T here tells the software to take the transpose of the matrix nu. and that's going to be dotted against the rate matrix. So this is basically the software doing what we have previously been doing by hand. I can then write my mole balances. That's going to be accumulation is equal to flow rates coming in minus flow rates coming out, plus the reactor volume times the net rate. At this point, it's going to be a column vector. So this is a column vector, this is a column vector, this is a column vector, all with 5 entries. And then I'm going to return this value, and I need to remove some of the matrix formatting in order to pass it to fsolve. You can probably just ignore that piece as long as your code is working for you. Okay, so I want to pass this to ssolve or fsolve. To do that, I need guesses for all of the different molar flow rates. So essentially, I need guesses for these 5 values. I've guessed here concentrations, and then I'm going to multiply this by the volumetric flow rate. That's going to give me molar flow rates. Alternatively, you could delete this piece here and guess molar flow rates in here. That would be fine. But what you're doing here is making a guess at what either the concentration or molar flow rate of species A, B, C, D, and E are exiting the CSTR. We happen to be lucky in this example because we already know the answer, because we already solved, or we were given that information when we looked at this problem another way. So I'm going to copy in those values here. But we didn't know this species E, right? We didn't know what its concentration would be, for example. So I had to make a guess there, and I just kind of guessed something, right? So usually you can make a guess, and as long as you're somewhat close, your problem will solve. If you don't get a solution, try, altering your guess a little bit, but don't worry too much about it unless you actually have problems. Okay, this right here is the code needed to run the fsolve command. Actually, it's this piece right here. You're going to use fsolve. You're going to tell it to run the CSTR function, which is what I've defined up here. You have to give it your guess. And then the other piece that I include here is the arguments that I include in the CSTR function. So basically, when you run fsolve, it's like, what are the equations I'm going to solve? Those come from running the CSTR function. And then what is the guess for the independent variables, or I guess the dependent variables? And so you're going to feed that information. Anything beyond here, this is basically information that I've defined in my function. I essentially just copy this information. So I don't copy in the X, but I'm going to copy in the other things that the CSTR function draws. So basically, the CSTR function is drawing that information from elsewhere within this code. So I include this both in the arguments here and also when I call the function here. All right, so once I do this, I now have answers. They're going to be stored here in this variable sol. And again, this is going to give me my molar flow rates. If I want concentrations from those, I can divide by the volumetric flow rate. And because this is a liquid system, I can divide by the inlet volumetric flow rate. And then I'm going to print some things. I'm going to print the final concentrations. I'm going to see how close the final concentrations are to the, I'm going to see how close my guess is to the final answer. So my guess, or my final answer, is molar flow rate. So I'm going to take my X guess, which is also molar flow rates, and see how close I was. And then I'm going to calculate out some other pieces of this. None of this is necessary. Once you have your answer, you have your answer. But if you want to check, here are the different concentrations, which I get from this concentration vector that I've created. And I can use this to reset up my net rate equation as well as my mole balances. And what I want to do here is determine what the accumulation values go to, because what I want them to be is 0. As you can see here, I've already solved for this, but if I push this, I should get a solution. We see the repeat of my stoichiometry matrix. So if you're having problems, first thing to do is check that, make sure you got it right. I already entered it in properly. This is my vector of inlet molar flow rates. So I had species A coming in at a concentration of 3 molar and a molar or volumetric flow rate of 100 moles per minute, and nothing else coming in. So that looks correct. Here are my final concentrations. This is the answer. These look pretty close to my my guess values, except for this species E. Since I didn't know that value at first, I guessed pretty poorly, but as you see, we still got a solution. And then here I have This is going to be the guess flow rates minus the actual flow rates. So as you see, most of these values are close to 0 with the exception of species E, given that I was not very good at guessing that. Finally, these are the accumulations. As you see, they're all on the order of 10 to the minus 10 or even smaller than that. That's close enough to 0 in my eyes, which says that this is a successful solution. We found the concentrations of A, B, C, D, and E that satisfy the steady state solution to the CSTR. And those concentrations are here. And if we wanted to get the molar flow rates, we can multiply by the volumetric flow rate, which is 100 liters per minute. So essentially multiply all those things by 100. And that's it.